he's going to talk about, well, he's going to introduce MUSR, spin rotation and relaxation. Thanks.
Okay, thanks, Ed. So I'm giving two talks this morning. The first one is this introduction to MUSR, and then there's going to be a slightly more technical talk on analysing MUSR spectra. So we'll have a short break in between, but this is the first one, telling you about the technique that you can do here at ISIS and also at PSI, muon spin rotation. You've already had an introduction from AD. What I'm going to be talking about is setting muons in their context, which I'm going to give you a bit of a history lesson. The historical context, I think, is quite interesting. I know we're all scientists here, and therefore not at all interested in history, but there's a little bit of interesting history here, because muons were originally misidentified. And I think there's an important lesson in the history of science, which is that history always repeats itself, as somebody once said. It has to, because no one listens. So muons were first studied in cosmic rays. Now, of course, they're produced in large accelerators, like the one that we have here at ISIS. But to begin with, they were studied in cosmic rays. So here's the story of the muon. It's the secret agent that we drop into enemy territory, which in this case means your sample. Like a good secret agent, it goes into enemy territory, it listens and finds out what's going on, and then it reports the information disappearing without a trace. And that's essentially what the muons do. So, of course, you know that the muon spins. So you have these two detectors. So here is the muon spinning, and every time the spin points towards a particular detector, we pick up a signal. So that's how I think about the muon. Okay, there are a number of different techniques that you can use with muons, depending on whether you... they've all got interesting acronyms, and again, you'll have access to all of these slides at the end of the meeting. I think that's true for all of the talks here at the conference. So there are a number of different ways of doing the muon technique. You can use transverse field MUSR. You can Fourier transform that data and look at the Fourier transform of this. You'll hear a talk from, I think, Francis Pratt later on in the meeting about how you do that. You can use radio frequency techniques, and this is something that's been really developed strongly at ISIS. People like Steve Cottrell, very heavily involved with that. You can measure in zero field or longitudinal field. You can do avoided level crossing. Again, you'll hear more about these techniques later. You can even, and I don't think we'll hear about that this time, use spin echo. This is a picture that Jess Brewer, one of the muon scientists in TRIUMPH, developed, just to sort of summarize the kind of data that you can get with MUSR. But let me take you right back now, before we look at the details of how you do a muon experiment, just to talk about the way a muon originated. And it was the physicist Rabi who, when the muon was discovered, said, "Who ordered that?" A little bit like when you're at a restaurant and a dish arrives and you have no idea where that one came from. I'm sure we didn't order this. So the muon's arrival was completely unexpected, and even great physicists like Rabi just had no idea where it came from. Let me talk a little bit about the discovery of the muon. So I'll wind right back to the end of the 19th century, and Röntgen discovered X-rays in 1895, and this was probably the first discovery that showed that a lot of the 19th century physics, where people like Lord Kelvin was saying physics is finished, we've done it all, we can pack everything up and go home. Physicists often say this when they reach a particular age. They feel that everything that they've discovered is it, and there's nothing more to find, so this is not a unique thing. But X-rays came along, and these were also a very unexpected discovery. And then a year later, in 1896, Henri Becquerel discovered radioactivity. So the 1901 and 1903 Nobel Prizes went to these two people. And again, radioactivity was completely unexpected, and it led to a whole series of new discoveries looking at radioactive sources, discovering, for example, that radioactivity didn't just come from a radioactive source in the lab, but also came from the sky. And in the early part of the 20th century, late 19th century, the bit of apparatus that you would use, rather than something like an ISIS spectrometer, the kind of standard thing that you'd have in your lab was this thing, an electrometer. Now, you may have not seen an electrometer, but at school I remember using a gold leaf electroscope, and it works on a similar principle. So have you seen these kinds of things before? Yes, okay, at least one person has. So now what you have in a gold leaf electroscope is you have a piece of metal in an insulating box, which is often wooden. It might have a glass front and back so you can see it. And there's a little piece of gold leaf that I've drawn here. And what you do is you charge it up, and the two pieces of gold leaf move apart. Now, if there's ionizing radiation present, what happens is that charge can leak away because the air becomes conductive. And so the gold leaf electroscope discharges, and the high-tech version that people had at the beginning of the 20th century was this thing, which is essentially the same thing. You now have, rather than gold leaf, you have some quartz fibres which are metallized. They have metal particles on the outside. And you have a microscope, and you can look through the eyepiece of the microscope, and you see the same thing. And with your electrometer, or your gold leaf electroscope, you can take it places. And one place you can take it, if you're in France, is the Eiffel Tower. So a Jesuit priest called Father Theodore Wolff, who was also an amateur scientist, in 1911, he took it to the top of the Eiffel Tower and discovered that it discharges more quickly at the top than at the bottom. And he was a good scientist because he also did a measurement over here. In other words, it was nothing to do with the Eiffel Tower and how close you were to its base. So moving in a horizontal direction made no difference. But going to the top of the Eiffel Tower, your electrometer discharged more quickly. So it was something to do with altitude. So this was the first discovery that it was a little bit more radioactive at the top of the Eiffel Tower than at the bottom. And you could then go a little bit further. This intrepid scientist, Victor Hess, who got the Nobel Prize in 1936, he took his electrometer on a balloon flight. So he went a lot higher than the Eiffel Tower. He went up to sort of 10,000 meters without oxygen. It was extraordinary. He did all these high altitude balloon flights and discovered that this effect was even stronger when you went to higher altitudes. Those of you that have flown here to get to this meeting will have been exposed to more cosmic rays because of being at high altitude in a plane. So again, I hope you can recognise this scientist. Yeah, that's right, it's Robert Millikan. So Robert Millikan is very, I don't know who the person on the left is. The person on the right, Robert Millikan, you may know him because of the oil drop experiment. He was the chap that discovered that the charge on the electron was quantized, that therefore electrons were quantized. We slightly fudged the results, actually. He founded Caltech, and he was the first person to use the term cosmic rays. He recognized that this radioactivity as a function of height was all to do with something coming from space. So he called them cosmic rays. He had a strange idea about the music of the spheres, which is an old Greek idea. So he had some rather wacky ideas about what cosmic rays actually were. Here you can see Robert Millikan talking to somebody. Anybody recognise who that is? Marie Curie, yeah, well done. And just over here on the right, Heisenberg, yeah, well done. Okay, some students of history of science here, very good. Okay, now here's Robert Millikan with his balloons. He cleverly worked out you didn't have to go in the balloon yourself. So he made these radio-controlled balloons, so they could go up to high altitude, and he could stay in Caltech drinking coffee. He could also send these detectors down into the ocean and discovered that as you went deeper underwater, the cosmic rays got less. So again, this was something coming from space. And of course, he realized that, as any of your supervisors, those of you that are PhD students, have clocked, that if you really want to make progress, you need a research student to work for you. So Robert Millikan, one of his great contributions was to have some really smart research students. So here is Robert Millikan with his research student. This is many years later. His research student was Carl Anderson, and here you can see an elderly Millikan with Carl Anderson and somebody else. And here is Carl Anderson in his lab. So what Anderson did, you can recognise here a magnet producing a magnetic field in this direction, and there's actually a cloud chamber inside the magnet. And what Carl Anderson is doing, rather than having nice ISIS scientists to produce a beam for him, he was just waiting for cosmic rays to land from the sky in his apparatus. He was applying magnetic fields and electric fields and all sorts of things like that to bend the particles around to try and work out what they were. And he made a big discovery with his own research student, actually, Seth Nedemeyer, and they discovered a particle in 1931 which they called the mesotron. Okay, spoiler alert, this is the muon. Okay, but it wasn't called that then, it was called the mesotron. They worked out that it had a mass of about 200 times the electron mass. Okay. Now this is Seth Nedemeyer, who also made the discovery. He was, as I said, one of Anderson's grad students. He subsequently worked on implosions later on in his career, as you can see if you look later on in his career. This is afterwards. He worked on a lot of the timing mechanism of the atomic bomb in the Manhattan Project. Here you can see him, an elderly Neddermeyer, receiving the Medal of Freedom, I think it was, from, again, I don't know if you recognise that historical figure before your time, but that's Ronald Reagan. So again, this is potentially the reward for a career in muon physics. So I lay this open to you. You may end up meeting the president, but maybe wait for a later one. Okay, now, the crucial historical message of this talk is that it's a dangerous thing when theory agrees with experiment. Okay, this is something that you should keep in the back of your mind next time your data agrees with some beautiful theory. It's a dangerous thing when you get perfect agreement because it may be entirely fortuitous. And the problem is that the discovery of the mesotron, as it was then called, agreed with theory. Now, a slightly technical slide, probably a bit too small for anyone at the back to see, but this is Yukawa on the right, a brilliant Japanese theoretical physicist who, as you can see there, got the Nobel Prize in 1949. He had worked out a brilliant theory of the way that the nucleus holds together. And it was based on the ideas that had been developed in the 20s and the 30s of quantum electrodynamics. Now let me just briefly explain what that was all about. Quantum electrodynamics is all to do with the way in which electrons repel each other or electrons and protons attract, electromagnetism. That interaction is carried by virtual photons. So two particles will attract or repel because of the exchange of a virtual particle. And quantum electrodynamics, which puts mathematical flesh on those bones, is the most brilliantly tested theory in physics. It's tested to 12 decimal places or something. So it was a great theory, and it was known even then how wonderful it was. But there was a puzzle. What keeps the nucleus together? The nucleus is a whole bunch of positive particles like protons that should repel each other, and neutrons that don't have any charge at all. So what on earth keeps the nucleus together? And Yukawa had a very good idea. He said, well, maybe it's just like quantum electrodynamics. It's the exchange of virtual particles. Maybe not the exchange of photons, but maybe the exchange of some other particle. And then he basically said, okay, we can do an estimate, and he did much more complicated maths than this, but this is my back of the envelope version of it. If you're going to hold the nucleus together, what you essentially need to do is, if you've got a proton on one side of the nucleus and a proton on the other, and they're attracting, and they're exchanging virtual particles, maybe these virtual particles have got mass, and therefore to make a virtual particle, you need to borrow a bit of energy from the universe, mc squared, to make the virtual particle. It will then travel across to the other particle, and then you can give the energy back. So all you need to do is borrow from the cosmic bank manager. Now, you may be a bit worried about the conservation of energy, but in fact, as Heisenberg showed us, there's an uncertainty relation. You can borrow a certain amount of energy for a certain amount of time, as long as the product of those two doesn't exceed h bar. That was the basic idea. So you can do a back of the envelope calculation and say, well, the amount of time you need to borrow it for is roughly a distance divided by a speed. So the distance is the size of the nucleus, and then how fast do these virtual particles travel, maybe about the speed of light. So you can put those numbers in, and then you can just crunch it, rearrange for delta for the energy that you need to borrow, and you get an energy of about 100 million volts. Or if you convert it into mass, 200 times the electron mass. Okay, that's exactly what Anderson and Neddermeyer had just discovered. They found a new particle which has a mass of 200 times the electron mass. Therefore, their particle must be this thing that holds the nucleus together. So this is what I mean by saying it's a dangerous thing when theory agrees with experiment, because this conclusion is not correct. Now, we're still in the 1940s. This is a rapid survey of history. But one of the next big things was that Bruno Rossi in MIT, in 1942, in the middle of the Second World War, measured the lifetime of these particles using a coincidence detector and discovered that they lived for about 2 microseconds. So these new particles, we've got a lifetime. And then the next thing was done by this chap, Marcello Conversi. Now I should say a little bit about Marcello Conversi. One thing that you might be amused at doing sometime is to work out your scientific lineage. Because you have a PhD supervisor, those of you here that are PhD students, and your supervisor had a PhD supervisor, and they had a PhD supervisor, so you can construct a family tree. And that's an amusing thing to do sometimes. So let me just show you this family tree. This is an interesting one. So if you start off at the top with Liebig, Liebig is famous, of course, for his Liebig condenser that you may have used in chemistry at school. He's also actually famous in Britain because he actually invented something that here we call the OXO cube. I don't know whether OXO is well known in other countries. Maybe you've no idea what I'm talking about. But anyway, Liebig started a company which made OXO cubes, so the patent came from him. One of his PhD students was this guy called Regnault, who you probably may know because if you've done thermodynamics, you would have used the gas constant, R. And the reason it's called R is after Regnault. Ah, yes, yeah, interesting. Now, if we go a few generations further on, you come to Bruno Rossi, who, as we saw, discovered the lifetime of the muon. And then if you go further down from Rossi, a number of his PhD students, Marcello Conversi, who I'm about to talk to, is here. There was a number of Nobel laureates, so Carlo Rubbia, who discovered the W and Z bosons at CERN, and then Giacconi also got the Nobel Prize, and Leon Lederman, another Nobel laureate, who I'll come back to later, because he played another crucial role in the muon story. So, of course, the first thing to say about muons, that you all know, I think, is that muons do not diffract. So often you'll hear people talking about muon scattering. They're wrong. Okay, muons don't scatter. It's not like neutrons. So the muons implant, and they stop somewhere in the sample. So they'll stop at particular sites in the sample, like the tetrahedral site in silicon or the body-centered site in silicon. I often say to people that, you know, in MUSR it's like darts and not squash, because the ball stays in, if you like. It sticks there, it doesn't bounce back. So it's not a scattering experiment. But what Conversi, Pancini and Piccioni, the various collaborators, did, publishing in 1947, but extraordinarily, these experiments were done in the basement of Vatican City in the middle of the Second World War. So I believe what happened in Italy is, during the Second World War, is many of the physics departments closed, and they all moved to Rome. So they concentrated all the research efforts there. And in Rome, there wasn't enough room in the various university departments, so various people got assigned their experiments into basements in spare space. So Conversi and these other people, they worked in a basement in Vatican City to do these experiments. And so they did something rather similar to what Bruno Rossi did measuring the muon lifetime. They had, this is their apparatus. And essentially what they were doing is they were waiting for cosmic rays to come into the experiment, and then what they were doing is stopping them in various different materials and measuring the lifetime. And these are their results. So what they basically found was, when you put these cosmic ray mesotrons into matter and measure their lifetime, if you put mu plus in anything, you get a lifetime of about 2 microseconds. If you put the negative versions, mu minus, into something with low atomic number like carbon, the lifetime is 2 microseconds. If you put mu minus into lead, the lifetime goes down to 0.07 microseconds. So there is a small effect that you see in lead, but basically, when you put muons in anything, the lifetime is not affected. So if we go back to Yukawa's idea, if this particle, the mesotron, really was the thing that held the nucleus together, if you fire it into matter, then it should just be gobbled up. It would strongly interact, and therefore you'd see huge lifetime changes when you put these muons into matter, and you basically see no effect. The only very small effect that you see, which I've just written down here, it's a minor thing, but basically the mu minus, the negative particle, and I don't know, Adrian, are you talking about mu minus later in this meeting?
Yes.
Yes, so you'll hear more from Adi about what you can actually do with mu minus in matter. But basically, what happens is that mu minus, being a heavy particle, it goes into the 1s orbit of an atom, it goes right down, kicks an electron out, and you may get some X-rays, you'll hear about this later. But basically, the mu minus can get captured by the nucleus, a proton will turn into a neutron, and that's what's responsible for this tiny change in the lifetime. But basically, there's no effect. And so what Conversi, Pancini, and the other chap, whose name I've forgotten, showed was that these particles are not strongly interacting enough to be the Yukawa particle. So the mystery was finally solved by Cecil Powell, a British physicist at Bristol, who in 1947 went up mountains and discovered a new particle called the pion. And the pion is the exchange particle inside the nucleus. It has a rather similar mass to the muon, but that's the thing that's really responsible for putting the holding the nucleus together. So this is really the picture that we have of cosmic rays. It's a bit small, so I'll just blow it up. So we have a lot of high-energy particles that exist in space. They come out of the sun, they come from the galaxy, various astrophysical origins. They collide with the outer atmosphere, and they produce a shower of particles. So you get protons and electrons and pions and all kinds of bits and pieces. The pions are very short-lived, so the pions only last for something of the order of 26 nanoseconds. They'll then decay, and then they'll produce muons. So the reason you only see the pions at the top of mountains is because most of the pions have gone down here. They've pretty much all gone at this level. But the muons make it down. So if you have not done MUSR before you started your PhD, you probably thought that the only role that muons play was to give you an example of something in special relativity. You know, this thing that cosmic ray muons live much longer than you think because they're travelling at very high velocity. And if you come from a background in particle physics, you'll know muons as a nuisance because they're the dominant component of cosmic rays. So many of these particle physics experiments that are looking for unusual WIMPs or strange particles, they go deep underground in the bottom of mines, very, very deep underground, so they can avoid the muons. So the muons for them are a problem. So again, if we just now zoom up in the picture, all the particles that are getting down now to ground level, this is the Eiffel Tower, this is, these are the muons that make it down to ground level. So in fact, if you plot the number of particles that you get at ground level, you find that we're basically sitting here. If you're at cruising altitude of a 747, you're roughly here. So actually at those atmospheric levels, you're probably getting more electrons in your cosmic rays, but down at ground level, the dominant component is muons. Roughly, we're getting 1 muon per square centimetre per minute landing on us right now. So it's a little bit like gentle rain. You know, that rain you can feel when you just get it on your shoulders and you think, yeah, I think it's starting to rain. That's the kind of flux that you have from cosmic ray muons. And they're quite energetic, actually. So most of them go straight through you. These are energies bigger than 1 giga-electron volt. Okay, I've pretty much finished with history now. I'm going to stop my historical story because we've got now to around this period. So the muon discovered here, the pion discovered in 1947, and of course particle physics has carried on going. So we are going to be focusing entirely on muons in this meeting, where we're thinking particularly about the uses of muons. And I guess as solid-state physicists and chemists, what we particularly might want to do is compare the muon with other particles that we know, so the electron and the proton. Now, electrons are normally negative and protons are normally positive, but of course you can make them in either charged state. So, and the same is true with muons. You can make negative or positive ones. We will predominantly be thinking about positive muons for most of the applications that we will be talking about. They're all spin-1/2 particles. The mass of the muon, 207 times the electron mass, is intermediate between that of the electron and the proton. That means the magnetic moment is intermediate between the electron and the proton. Remember that the magnetic moment is roughly proportional to 1 over the mass. So therefore, the more massive the particle, the smaller the magnetic moment. And this is going to turn into this very useful number, the gyromagnetic ratio. Gyromagnetic ratio tells you essentially the link between angular momentum and magnetic moment, and it also tells you how fast these particles will process, their spins will go round and round in a magnetic field. So a very, very useful number to remember when you're doing MUSR is 135.5. That's the number of megahertz that you get per Tesla. So you can turn a magnetic field that you get on your in the MUSR experiment and convert that into a frequency. But then, of course, the big difference is the lifetime. These may not, in fact, be infinite. They may be just enormous numbers, but they are certainly bigger than the 2.19 microseconds that you have for the muon. Okay, I'll skip over that. So let's think a little bit about how you make muons. You'll hear probably a little bit more in this meeting about the production of muons. I think you have some talks about some of the practical aspects of the way the beamline works later on, and certainly how you build a spectrometer is something that you'll be doing later. But let's think a little bit about how muons are made. We generally are not going to be finding that the flux from cosmic rays is large enough, which is why we have to now do our experiments at high intensity accelerators like the one here at ISIS, like the one in PSI. ISIS produces a beam of protons. The protons hit a carbon target, and that produces pions. And the pions, as we've said, decay very quickly in about 26 nanoseconds. And the thing about pion decay, it's a two-body decay, and it decays into a muon and a neutrino. Being a two-body decay, that means if you think about a stationary pion, the muon will go one direction and the neutrino will go in the other direction. Now there's a strange quirk of particle physics, which is that the spin of a neutrino is always anti-parallel to its momentum. Therefore, the muon has to do exactly the same but opposite. So its momentum goes off in the other direction. And because this thing has zero spin, the spin of the muon is also anti-parallel to its momentum. So this is hardwired into the experiment. Okay, now we'll be thinking in this talk at least about the pions that decay at rest on the surface of the target. These are called surface muons, and the ones that you're generally measuring at ISIS. Now, if the pion is initially at rest, you can do a little calculation, which I think is first-year relativity in many physics courses, and you can work out what the energy, the momentum, and the speed of the muon will be in those different cases. And the numbers that you get out, an energy which is roughly the rest mass energy plus 4 million electron volts. So your muons will be coming in the beam with an energy of 4 million electron volts. The speed is roughly a quarter of the speed of light. So they are really zipping along at great speed. And also we see that the muon beam is 100% spin polarized. Now, it's also possible to look at the muons that come from the pions that decay in flight. They have a bit more forward momentum. What you basically find is that they have less polarization, but of course higher energy, higher than the 4 million electron volts. So they will penetrate into your sample further. So if you want to do experiments at high pressure, for example, and you need to get your muons into a pressure cell, or maybe some big chemical reaction cell, something with thick walls, then you'll have to use decay muons. For example, at ISIS, all of the muon beamlines on the south side, the European community side, those are all surface muons. Okay, just so it's in your notes, and if you've forgotten, this is how you derive those results, but I'm not going to go through that now. Okay, step 2, now you've got your muon beam, you implant them in your sample. So the muons fire into the sample. They then go through a whole series of slowing down processes. So they'll ionize some atoms, they'll scatter some electrons, they go through a series of electron capture and loss processes. So they'll pick up an electron and then shed it, pick up an electron and then shed it. And their energy will sort of wind down, so you'll go from about 4 million electron volts down to a few electron volts. Now this looks like a complicated process, and it is, and there's quite a lot of physics in this. But the good news for us is that this process involves charge degrees of freedom. In other words, the charge on the muon and the charge on other things, but it's not magnetic. So even though the muon is being bashed around, its spin stays in exactly the same direction. So by the time the muon slows down and sits somewhere in your sample, after having gone through the cryostat windows and everything, the spin is still locked in place. And that's very good news for us, because it means we generally don't need to worry about these slowing down processes. The muon spin is preserved. And then the third thing that happens is decay. So if you put in, as you can at ISIS, a whole bunch of muons at time t equals 0, and then you wait as a function of time, what you will see is that the number of counts in the detectors goes down exponentially. It's just radioactive decay. And every single experiment that you do here at ISIS will look exactly like that. Okay, so that's the end of the story. We can all go home. Very boring. Except, of course, just by summing all the detectors, even though every single experiment on every single sample will look like that, of course, the really interesting thing that we can do is think a little bit harder about muon decay. Muon decay is much more leisurely than that 26 nanoseconds of the Pion decay. So 2.2 microseconds seems like a short amount of time, but in particle physics it's pretty much forever. It's a huge time because the muon is weakly interacting. When the muon decays, it goes into a positron and a couple of neutrinos. This is three-body decay. This means it's a bit more complicated than what we were looking at in the last section. So there's a number of ways of partitioning up the energy from the muon. So you can basically have no energy going into the positron. This stays stationary, and the two neutrinos carry off the energy, or maybe the positron goes off in one direction and the two neutrinos go off in the other. So there's a range of energies that you will get from your positrons which are emitted. But of course, there's even though there's a range of energies, there's something really crucial. And this was discovered essentially by Richard Garwin, who now works for, I think, the US Defense and does all kinds of complicated things to do with strategic nuclear stuff, or hush-hush. And he also worked with Leon Lederman, who for many years was director of Fermilab and got the Nobel Prize for his work discovering some particles, J-psi particles. So here's Leon Lederman, got the Nobel Prize in '88, director of Fermilab. He also wrote a rather entertaining book called The God Particle. If the universe is the answer, what is the question? This was just before the discovery of the Higgs boson. It was when they were going to discover the Higgs, they thought, at a big accelerator they were going to build in Texas, which got cancelled by the Clinton administration. So in fact, if you read this book, he talks about the river of science that, again, I'm afraid this is only visible to people at the front, but started with the Greeks, goes through Galileo and Newton, through Faraday, Maxwell, Bohr. There are a number of little tributaries that go off in sort of uninteresting areas like electrical engineering, mechanical engineering, nuclear science. You can see how he thinks. So this river goes all the way through Schrödinger and Fermi and Feynman, and then goes all the way to Fermilab and the lab they were going to build in Texas, which got cancelled a few months after this book appeared, which shows you the role of hubris. Anyway, back in the late 50s, Garwin and Lederman were collaborating. What essentially happened, it's a great story. Madame Wu at Columbia was just about to make or publish her breakthrough result on parity violation in beta decay. And the tradition in Columbia University was that everybody went out for a Chinese meal on Friday. And Lederman was there and heard about this, and suddenly realized that muon decay would do the same thing. So he quickly called his friend Richard Garwin, who had a PhD student called Weinrich at a particle physics lab near New York. And so this poor PhD student, who'd been working on this apparatus for a year, was told over one weekend to dismantle all his apparatus and set it up for demonstrating parity violation in muon decay. This is essentially the experiment that you do. You'll do this experiment essentially later on this week, because you'll. And this is how Lederman described it in his book. So you can see he was good at hype. Now, essentially, what they did was they just saw a basic MuSR experiment. They got the muons to precess, and they were able to show that the decay of the positron was asymmetric. And so the principle they were basically following is the following. This is the kinetic theory of gases. Particles bouncing around in a box, like if you have a chamber of gas bouncing around in some container. If you view that process in the mirror, then of course all of the bounces, you see the mirror image. Nothing violates the laws of physics. So it's hard to say whether this is the real one and this is the mirror image or vice versa. And most processes are like this. If you view them in a mirror, they basically show you completely valid processes in nature. The muon decay, on the other hand, is not. So if you see a muon, here it's spin, and I'm showing you here the sort of angular momentum going round and round. When the muon decays, the positrons are primarily sent out in one direction. If you view this in a mirror, the spin is in the other direction, because you can see this rotation turns into that rotation. So the spin reverses, and now the positrons are shot out of the back end. And unusually in physics, this one occurs in our universe, this one does not occur. So the mirror image is not an allowed process in nature. And this is what you see in beta decay. Madame Wu saw this, but this is what Lederman and Garwin and Weinrich discovered in the late 1950s. It applies to muon decay as well. In fact, this is an easy experiment to do. It shows it more dramatically. The two papers were published back to back. Now, Wolfgang Pauli didn't believe it. And he said, "I cannot believe God is a weak left-hander." He didn't like the idea that there should be this, right-handed or left-handed, this breaking of symmetry. Some of you may have discovered that in the coffee and tea earlier on, because the two pots look identical, but if you try to pour your drink, you realise that they're not, and they're not labelled, they're completely identical. So parity is broken there as well. Okay, so this is the picture we used for the 2005 Muon conference in Oxford. This is Alice in Wonderland, and you can see her here playing with muons. If you know Alice in the Looking Glass, you'll know this is a very appropriate image to use, because she was fascinated, as Lewis Carroll was, with mirrors. Okay, so this is now our picture that the positron decay of a muon is asymmetric with respect to the initial muon spin polarization. And it's a slightly more complicated picture than that. This shows you the muon spin. These different curves show you the probability of positron emission for different angles, and the different curves show it for different energies. Remember, I said that you can partition up the energy of the final decay positron in different ways, all the way from 0 up to some maximum. Here I'm using epsilon to be E over E maximum. And if you average over all energies, you get this blue curve here. And you can see that there is a larger preponderance for the positron to be emitted in the same direction as the muon, much more so than the backward direction. And if you look in their paper in 1957, they point out they said it seems possible that polarized positive and negative muons will become a powerful tool for exploring magnetic fields in nuclei, atoms, and interatomic regions. And that essentially is the foundation of the technique that we are using now, and that was recognized by these three people in 1957. Okay, so I'll just say a few things about muon spin precession. As I mentioned earlier, the gyromagnetic ratio here, gamma, that we've been referring to, is the thing that links magnetic moment to angular momentum. This is essentially because when charge orbits, like an electron going around an atom, you've also got mass orbiting as well. And so the gyromagnetic ratio tells you that ratio of charge to mass, and you can see the gyromagnetic ratio has a form in it which is charge divided by mass. There's a factor of 2 in there as well that you also need because of the different ways in which these things are defined. But again, the gyromagnetic ratio is telling you about this relationship between magnetic moment and angular momentum, but it also tells you about how fast things precess. And as I said earlier, this is really repeating what I mentioned earlier. Again, here's the nuclear magneton and the Bohr magneton, the magnetic moment of the nucleus, the magnetic moment of the electron, and here are the numbers for the proton, the electron, and the muon. And yeah, this probably slightly more accurately should be 135.5 megahertz per Tesla, telling you how fast something precesses in a magnetic field. And so what this means is, if you measure a frequency, you've measured a field, because of this linear relationship between field and frequency. This works for electrons spin resonance, for nuclear magnetic resonance with protons, and with μSR. I've already done this one. Maybe just very quickly to show you this picture. in a muon experiment, the muon is pointing towards the backward detector when it comes in. I'll show you the number of counts of the backward detector and the forward detector. And as time evolves, you can see that the muon spins round. On average, you get this exponential decay. But if you look at the counts in the backward and the forward detector, you see them oscillating around each other, and you can then extract the asymmetry. So this is, if you like, the high-tech picture of the same thing. So in this little animation, the muon comes into the experiment. Here is the sample. The muon comes in backwards with its spin anti-parallel to its momentum. What you can see here is the spins pointing towards these different detectors. I've shown them lighting up when they trigger as the muons are pointing towards them. And this essentially is what we measure in the experiment. I made this animation on a dark day in winter, so you can see that I was imagining blue skies and the beautiful sea. But of course, the muon experiment at ISIS looks a little bit different. So these are rather old pictures. So of course, the experiments are done here at ISIS. You can do them at the Paul Scherrer Institute. And there are these 4 places in the world where at the moment you can do muon experiments, although more are being built. Korea, in China, in Japan, possibly in the States. But these are the 4 main mature facilities at the moment where you can do muon experiments. Okay, I think time is moving on a little bit, so I think I will do these very quickly. So you'll hear a little bit more from Tom Lancaster tomorrow about muons in magnetic materials, but this is just an example that some of us, I see Francis at the back, that we studied back in the 90s. These are organic materials that show magnetism. So the thing I like about these data, first of all, they are very clean and beautiful. Secondly, they're done at very low temperature, and this demonstrates that the facilities here at RAL are perfect for measuring very low temperature data, because you can just have a dilution refrigerator and have it dangling in the muon beam, and it works. And because of the brilliant cryogenic engineers, who I see are also here at the back, these things work. So what you can see in these data are these oscillations as a function of temperature, high temperature, 700 millikelvin, the balmy temperatures there. All the magnetism has disappeared, and you just see a slow spin relaxation. See, these 2 materials are ferromagnets and antiferromagnets. Well, what you can do is plot those frequencies as a function of temperature, and what you see is that these frequencies get slower as you warm up. So you can see this here, the frequencies are getting slower and slower until they disappear. And of course, because you've got this linear relationship between frequency and field, I can also label these graphs with field on the other axis. So what we've got is a definite measurement of the magnetic field. Here you can see it's about 15 millitesla in this compound, goes all the way to 0 at 700 millikelvin, or just below 700 millikelvin. And these materials were interesting, particularly this one, because it was the world's first purely organic ferromagnet. And we were able to show that the whole of the sample was doing this. Very nice behavior using muons. Of course, what we're measuring, you've got magnetic moments, and you're measuring a magnetic field. So unfortunately, you're not directly measuring the magnetic moments. There's this dipolar tensor that takes this rather complicated form, which is connecting the magnetic moments to the magnetic field that you measure. Essentially, that equation looks rather complicated, but all it means is here's a magnetic moment, and here's the field that it produces. So if your muon is sitting somewhere over here, you'll see a magnetic field that's pointing in this direction with this intensity. Okay, now I have to do something on here to get this to work. So this is a beautiful image, I think it was taken by James Lord here at ISIS. So this is actually what the muon beam looks like. So you can see if you put a camera in the muon beam, the muons are largely here, but there's a few little other triggers that you can see further out. But this is what's hitting your sample. So we're not allowed to look directly at the muon beam, but anyway, this is what you see. Okay, I'm going to stop there. That's my summary. So that's the end of talk number 1. So maybe we just have any questions maybe at this point? Yeah.
So these are all charged particles, right? So how come they don't attenuate to the same extent when like sample holders and stuff, as you would for an electron in an electron microscope or something like that?
So first of all, they're heavier. So they're more massive, about 200 times the electron mass. They do attenuate over a fairly short distance. So once you have about 150 milligrams per square centimeter of material between the muon beam, that amount of material is enough to attenuate the muon beam. So that only really equates to something like a few hundred micrometers thickness of most materials. It depends a little bit on the density and the chemical composition. But something like that sitting in the muon beam is enough to attenuate it. And I think it's essentially due to the fact that the energies are higher. So 4 million volts is much higher kinetic energy than you typically have in an electron microscope, where you might just have 100 kilovolts or something. And also the particles are more massive. So fortunately, the whole field of the attenuation of charged particles in matter is a really well-developed field. And so you could do calculations of these sorts of things and see what they are with different types of particles. So it really depends a lot on energy and mass.
That's the same for the positrons that's coming out through the decay process.
Yeah, the positrons are coming out with even higher energy typically. So they seem to be much more, again, because they're lighter, they're typically coming out with tens of million volts of energy. So they will go quite happily straight through. I mean, a few will be attenuated, but they will come out quite happily from your sample and the cryostat tails into the detectors.
And also the low energy positrons are the ones that don't have so much information.
Yes.
So we're actually quite happy that we attenuate some of the low energy particles.
Yeah, that's it. I feel like I'm doing a lot of talking at you, so would you like to just take a break for a couple of minutes and sort of stretch your arms and legs, and then we'll maybe we'll just have a 2-minute stretch, if that makes sense, and then you can